Okay, so today we start with, so far we have looked at bipolar transistors and amplifiers made using bipolar transistors, amplifiers like common emitter, common collector, common base, output stage. And what we'll be doing in the next couple of lectures is look at MOSFETs, basic operation and device models. And then we'll look at similar kind of amplifiers built using MOSFETs, basic amplifier stages built using MOSFETs here. All right, so let's start our discussion related to MOSFETs. So today we'll look at basic operation of MOSFETs here. So let me remind you that one of the basic characteristics of a transistor, at the least a transistor must have three terminals, a pair of input terminals and then an output port here. And realize that the transistor must exhibit the following characteristics: that the output current is much more sensitive to input voltage here as compared to the output voltage here. So this is the characteristics that we are looking for in a transistor. Del I0 by del V in, which is the transconductance, and is much larger than the change in output current versus change in output voltage, which is the output conductance here. So to call a three-terminal device a transistor, we have to see that it exhibits this kind of a property here, that the transconductance is much larger than output conductance here. Alright, so the first thing to note here is that the device must exhibit transconductance, that the output current, besides depending on the voltage applied across the output terminals, must depend on a third pair of terminals here, which is the input here. Alright, so with that background, with that reminder, let's look at a transistor, which we call as a MOSFET. And if you look at the, if you expand the word MOSFET, it is metal oxide semiconductor field effect transistor. So the first thing to understand is this field effect principle here. What do we mean by a field effect transistor? Okay. And so with that in mind, let's take a N-type semiconductor. And N-type semiconductor, all of you know, will have donor atoms here, which are ionized at room temperature, at least. And these donor atoms give rise to electrons here. So I have all these donor atoms inside my semiconductor, along with I have all these minus negative charge here. The electrons are there. Okay. So we have all these donor atoms and electrons. And donor atoms, of course, are immobile. They're fixed in their positions. Electrons, of course, can respond to voltage and can move. So now suppose we do the following here. We have a bar of N-type semiconductor. We make two contacts. Two metallic contacts here. And we assume that the contact is an ohmic contact, which means easily allows electrons to pass through this particular interface here. Electron can enter the N-type semiconductor or exit the N-type semiconductor easily. There's no problem. Okay. So you make two contacts, two ohmic contacts, and then if you apply a voltage, say ground here, and you apply 5 volts here, obviously I have a lot of electrons here. When you apply 5 volts, the electrons are going to go from here to the 5 volt terminal here, and a current would begin to flow. Right? So I have a lot of electrons. You apply a voltage. The voltage creates an electric field. The electrons are pulled into the positive terminal here, and the circuit completes, and you have a current flowing. The amount of current which flows would obviously depend on the voltage that you apply. The larger the voltage, the larger the field, and more the current. Besides that, you can also easily appreciate that the amount of current would depend on how many electrons are there. Okay, the more the number of electrons, the higher the conductivity of the material, and the higher the current. All right. So that's so this one, a N-type semiconductor with two contacts here, it simply behaves as a resistor. It's a resistance. So if you plot the voltage here versus the current, if you plot it, you will see a straight line here. It obeys Ohm's law. V voltage equal to I times R, and R, as I said, depends on the doping, depends on the thickness, depends on the area, all of these the factors that we are familiar with. Okay. Now let's suppose we do the following here. We take another plate, metal plate here. We take another plate, and by some means, let's say you place it very close to the N-type semiconductor. Now what you do is you apply a negative voltage. Okay? You take another plate, place it very close to the N-type semiconductor, and you apply a negative voltage here. So negative voltage will do what? Will create a field, right? Negative voltage will create a field, and you know that if it's negative, what will be the consequence? Is gonna, if you apply a negative voltage, it will require a negative charge here, right? So what it's going to do is push the electrons away from here, from the surface. Okay? So what will happen is the following. These electrons that you see here, they're pushed out. Pushed out means what? Pushed out means they flow out through this terminal here, and they come back here, and this is the negative charge here. And positive charge is left here. So you're seeing that what you have is a capacitor. Something like a capacitor. This is one plate. This air or vacuum, whatever is there between, is like an insulator. And this is like the other plate. So when you apply a voltage to the capacitor, -2 volt, what happens is you require negative charge here. And what happens is these electrons from here, they go through this terminal and come over here. So the electrons line up here, leaving behind a positive charge here. So you get positive charge on this side, and you get negative charge on this. Okay, so it's basically like a capacitor here. But the consequence that you realize now, what happens is if I apply a negative voltage, it has removed electrons from close to the surface, and therefore I get a change. The conductivity alters. I have less electrons in my system here, and obviously less current will flow here. So what you see here is that I can modulate the number of electrons here by applying an electric field here. Okay? I can modulate the number of electrons and therefore the conductivity in this particular sample by applying an electric field here. And this is what we call as the field effect principle. That by applying a field, I can alter the conductivity. I can alter the amount of charge inside my semiconductor. So that's where the word field effect comes from. Okay? And you can also see now that this particular device exhibits transconductance. Why? Because now this is a 3-terminal device. I have a pair of terminals. Let's say this is the common terminal, and you think of this as an output terminal here, and you think of this as the input terminal here. So the current flowing between this terminal and this terminal here is controlled by voltage applied to a third pair of terminal here, a third terminal here, and therefore this particular device exhibits a property called transconductance. The current flowing here is controlled by not just this voltage here, the current flowing here is controlled by the voltage applied here. So it exhibits transconductance. Now, the next thing that we have to show, which we'll see later on, is that the transconductance under certain conditions can turn out to be much larger than output conductance here. And therefore, the device then becomes capable of voltage gain and other properties here. Alright, so that's the field effect principle here. Now, you go back in history and you find that the first report of field effect transistor or the first patent that was filed was in 1926 here for a field effect transistor. And you can read here, you can read it later on. It says the invention relates to a method and apparatus for controlling the flow of an electric current between two terminals of an electrically conducting solid by establishing a third potential between said terminals, and is particularly adaptable to the amplification and all that. So this person, Lilienfeld, is proposing a field effect transistor as a replacement for vacuum tube. Vacuum tubes were prominent at that particular time, and vacuum tubes were, of course, large and bulky and a lot of problems, and therefore people were obviously thinking for a replacement, and he had proposed a solution for that, which is the field effect transistor. So this was in 1926. So the concept of field effect transistor was there. People tried building it. They couldn't. They couldn't build the field effect transistor. And, in the attempt to build a field effect transistor, in the process of that, they discovered the bipolar transistor here. Point contact transistor and bipolar contact transistor here. So bipolar transistor was not anticipated like the way this guy is anticipating the field effect transistor. Bipolar transistor was actually discovered in the process of building a field effect transistor. So in terms of conceptualization, a field effect transistor came first, but people couldn't build it. People were successful in building a bipolar transistor. But then after bipolar transistor, efforts were continuously made to build a field effect transistor, and people were successful, especially with MOSFET in 1960s. And now, of course, most of the circuits are built with MOSFETs here. Okay. Anyway, so this is the transistor that we have. We said that if you take two terminals and you add a third terminal, place it over your N-type semiconductor, then you can, using this particular terminal, you can control the current which is flowing between these pairs of terminals here. Now, of course, how do you suspend a metal plate very close to the semiconductor? So you can't really, it's not easy, or if not impossible, it's not easy to do that. So what you do is the following. You realize that air only acts as an insulator. So what you can do is a very good insulator in a silicon system is silicon dioxide. So what you do is you deposit silicon dioxide and you put the metal on top. So here air was serving as an insulator. Here oxide serves as an insulator here. And then you end up obviously with a metal here, oxide here, and a semiconductor, metal oxide semiconductor. And we know that this device exhibits transconductance and is a transistor. And it's a transistor which is based on field effect principle, where you modulate the conductivity here by applying a voltage here. Okay, so that's how this particular device gets the name metal oxide field effect transistor here. So transistors then, based on what we have discussed so far, transistors can be classified in these two categories here. Bipolar junction transistor, which we've already seen in some detail, and then the field effect transistor here. And field effect transistor can be classified in actually many different categories. Even here you can have different kinds of bipolar transistors here. MOSFET is one of them here. And there are others. There is a junction field effect transistor called JFET. There's a MESFET, and there is a high electron mobility transistor and all kinds of other things as well. But most of them are all similar. They're based on similar principle here. And this, of course, is the dominant field effect transistor, MOSFET here. Okay. So we'll spend some time here looking at the operation of this one. Now, MOSFETs are also of different kinds. Okay. So here I'm talking about a MOSFET which we call as a depletion mode transistor. Okay, you'll see why the word depletion mode comes into picture, but let's look at the schematic here. So first of all, note that it is a MOSFET. There's a metal oxide semiconductor here. There are two terminals here, which we call as source and drain. The current flows between source and drain. You could think of that the source is the source of carriers, electrons. So electrons start from here, and eventually they're collected at the drain side here. So that's how it gets the name drain here, and this is the source of electrons here. Now, if you look at this particular transistor, so what you see is that the main semiconductor is p-type, and in that p-type semiconductor, there's a region which has been made N+. N+ means heavy doping, and this is source, and there's a region N+ again, heavy doping, which is drain. And there's a region close to the surface which is also N-type. That's not heavily doped. It's only N-type of a certain thickness. Most of the material is p-type. Okay. These things that you see at the surface, the N+, this depth that you see here. First of all, this silicon wafer would be something like 400 micron thick. Okay. So the whole wafer, silicon wafer on which it is being made is 400 micron thick, let's say in a typical size. N+ region may be, say, half a micron or even less. Okay. So this is like half a micron. This is like a half a micron. This may be the thickness of the N-type, maybe a few thousand angstroms, 0.2 microns or 0.3 microns. So what we are talking about is these transistors made right at the surface. The whole of wafer actually is just p-type. It doesn't do anything. It's just there for mechanical support. All the active action takes place right at the surface here. Okay. So the thicknesses, keep in mind, are in submicrons here. Submicron here, submicron here, submicron here. Okay. The current then would flow. Actually, you can see there's a direct path here from source. This is N-type, a lot of electrons are here. This also has electrons. So the current really flows from source to drain. I mean, the direction of electrons is from source to drain. The current would flow opposite to the direction. All right, so the current is then flowing at the surface here. Now, transistor must exhibit transconductance. So if I apply a gate voltage, what would happen is the following here. So let's see the operation. We apply 0 volt here. We apply 0 volts here, and we apply 5 volt here. Note that this junction is 0 biased, 0 here and 0 here. So this is 0 biased, and this junction is reverse biased here. So no possibility of any current flowing here. Okay, so this is 0 and 5. So obviously current will flow from drain to the source here. Electrons will flow through this particular layer. Now, so what happens is, if I apply a 0 volt to the gate, if I apply 0 volts to the gate, we have a channel here. We call this layer under the oxide as a channel. So we have a channel here, channel which is full of electrons, and current can easily flow between source and drain. Okay. Now you apply -1, negative voltage. So what happens is, at 0 volt then, a current flows between source and drain. If I apply negative voltage, note we already saw what negative voltage will do, which will repel the electrons from the surface here. Will repel the electrons, and therefore the conductivity of n-type will change, will decrease, and the current will decrease here. Okay. So let's see that thing in more detail here. So the idea is, channel exists at 0 gate voltage, and we apply negative voltage to the gate to deplete the channel, to deplete it of electrons. And that's how it gets the name depletion mode transistor here. So see what happens here. You apply -1 volt. What do? You remove all the electrons from here. All the electrons are removed from the surface, and the electrons are placed here on the metal. And of course, I'm not showing here, when you remove the electrons, you leave behind the ionized donor atoms here. So there's a positive charge. Now current can still flow. The current can still flow from the remaining part of the channel here. But the current will obviously become smaller, because I have the thickness of the channel has reduced, and therefore the resistance of the channel goes up, and I have lesser current in my system here. So current decreases. You apply even higher voltage here, you deplete even more of the channel here. You remove more electrons, so your depletion region is even larger here. And so you have even lesser current. And obviously you can see now, I can apply a sufficiently large voltage here, such that I remove the channel altogether. Okay, remove the channel altogether. Now, it should not give you an impression that, okay, so the colors are different, so it does not give you an impression. So you remove the channel, and therefore now the current goes to 0. So by applying a sufficiently large gate voltage, you can, what we call as, you can pinch off the channel. The channel is completely pinched off, and no channel anywhere in my device, and the current has gone to 0. So when we didn't apply any gate voltage, 0 volts, there was a channel which was existing. And we applied more and more negative voltage to do what? To deplete the channel here. And eventually, as we are depleting the channel, we are changing the current. So the device exhibits transconductance here. The current here responds to the gate voltage here. Eventually, you apply a large enough voltage, the channel simply disappears, and you get 0 current here. So you can see that this device can also act as a switch here. If I apply 0 volt here, I get a lot of current in my system. My transistor is on. If I apply, let's say, -3 volt, the channel disappears. I get 0 current here. So it's like a switch. You can turn it on or off. Okay. And also, because the current responds to the gate voltage, it changes with the gate voltage. It has a transconductance, and therefore, when it has a transconductance, we'll see you can build amplifiers and all of that you can do. Okay. So this is what we call as a depletion mode transistor. Again, why depletion mode? Because a channel exists at 0 gate voltage, and you apply negative voltage to deplete the channel and eventually remove the channel altogether. This is in contrast to, so this transistor is not very commonly used. Depletion mode transistors were used in the beginning, but they're not very common now in MOSFET. What is most common is what we call as an enhancement mode transistor. Also, it's a different kind of a transistor which we call as inversion mode. Okay, so let's try and understand. Let's look at the structure first. So I have a p-type silicon. That's my wafer. So here is my p-type silicon. And what we do is, well, there comes SiO2, but SiO2 doesn't come from the top. It can come to the top. I mean, what you can do is, you can have a system where you deposit SiO2 in a CVD chamber. You deposit SiO2, but normally what happens is, you take p-type silicon and you heat it up in an oxygen ambient, and the silicon itself oxidizes and becomes SiO2. Okay, so that's how normally SiO2 is put. And of course, this comes from the top. You evaporate metal, and you have a metal here, and then you make these regions N plus here and N plus here. So we have a MOSFET here. Okay. So it's a different kind of MOSFET that you see here. Earlier, we had an N plus, we had an N plus, we had a P. But remember, we had a layer here which was also N. We don't have that anymore. Okay. And you make all these, you evaporate metal also. And you attach your wires, and you have a source, you have a drain, you have a gate, and you have a body. And also note that this transistor is actually a 4-terminal transistor. Okay. Unlike bipolar, bipolar also had a substrate terminal if you think about it, but here is source, drain, gate, and body. Okay. So let's come back now to a 2-dimensional figure here. So we have a MOSFET, and note that there is no N-type layer here. And between these source and the body, I have a PN junction, and between this and also I have a PN junction. And let's assume that the body is ground, and therefore the PN junctions are either zero bias or reverse bias. Normally, nothing will flow here. Okay. So you can see here, if I put 0 here, and 5, this side of the PN junction is zero biased. This side of the PN junction is reverse biased. I don't have any current flowing in my system. So if I apply a gate voltage equal to 0, normally what will I see? Zero current. No current is flowing into my system. Okay. There's no channel. By channel, I mean, you see, if your source is N-type, a source is full of electrons, drain is also full of electrons. Channel means a thin layer here of electrons, which allows the source and the drain to be connected together. That's what we mean by channel. So in this case, what we are looking for is a thin layer of electrons between source and drain. So there's no channel. This layer is all P-type. Okay. And there's no channel, and therefore there's no current that flows in my system. So when you apply 5 volt here and 0 here, zero current. Unlike the previous transistor, where when I applied 0 here and 5 volt here, a channel was already there, and therefore a current was flowing. Okay. So now this is a better picture of what is really happening. I have N plus, I have 0 is here, 0 is here. I've applied 5 volt. And now what we want to see is what happens as I apply gate voltage. So now note that you want to create a channel. You want to create a channel. So create a channel means you want to create a layer of electrons at the surface. What voltage should you apply? Positive voltage, because you would like, wherever electrons are there, you would like to attract them to the surface, right? And create a thin layer here. And so we'll apply positive voltage here. Say I apply 0.2 volt, very small voltage here. What will this voltage do? Positive voltage now. And note, what are the predominant carriers in my system? Holes. All these are holes here. And these are acceptor atoms, which cannot move. Ionized acceptor atoms here. So when you apply a positive voltage, what will this voltage do? It's going to push the holes away, right? It's going to push the holes away, and this is what would happen. The holes will go away, and where will that positive charge go? It goes to the metal plate here. It goes to the metal plate here, and leaving behind this negative charge on this side here. Okay. So this is where it goes. Okay. And what is the path that it will take? You know, the body is there. It can easily go out through the body here and come back here. Okay. Because body is P-type, the holes can easily flow out through the body, come here and go and sit on the gate. So the holes have come and the positive charge is sitting here and I have negative here. What happens to the current? What happens to the current? Does it increase, decrease? Anything happens to the current? No? Okay. What you see is, what have I done at the surface? Have you seen that I've created a depletion layer? What do I mean by depletion layer? A layer which is depleted of carriers. Right? Now, originally this particular layer had which carriers? Holes. And it had very few electrons anyway. And now you have removed the holes also from the surface here. So this layer is depleted of carriers here. So I have a depletion region. Okay? I have a depletion region here. I'm drawing a dotted line showing that there's a depletion region. Now you apply even larger voltage. What will happen? It will remove even these holes. Right? So depletion region is found here. So you apply even larger voltage here, 0.4. Even these will go away. And my depletion region will move here. Right? I deplete even more. And I apply even larger here. But something interesting happens now. Depletion region is increasing. I'm depleting more and more of my p-type region here of holes. But then this is where is a very important principle here. Something interesting happens. As you are removing the holes, the electrons increase. The electrons start to appear at this particular point. Okay, where do these electrons come from? Okay, this is a very fundamental principle in semiconductors, that number of electrons multiplied by number of holes is equal to Ni square, which is a constant quantity. Ni is a fixed quantity here. So now note something interesting that happens here. As you reduce the number of holes from the surface, as P goes down, what happens? N goes up. N goes up here. So as you're pushing more and more holes away from the surface, electrons start appearing at the surface here, because they have to balance. They have to balance here. Okay. So at a sufficiently large voltage, now what happens is you keep on applying higher and higher voltage, more and more electrons appear at the surface, and you get a sheet of electrons at the surface. Eventually, if you apply sufficiently large voltage, and let's say we call it a threshold voltage, a sheet of electrons, fairly large number of electrons appears at the surface here, and you have created a channel. And what is the basic principle? So this region is depleted, and the electrons are there all at the surface here. Okay, and this is what we call as an inversion layer. Because note, what has happened is, I'll just show you in a minute, the surface has actually become N-type. The surface has become N-type. Now, realize what is the meaning of P-type, N-type, and intrinsic. Intrinsic is when number of electrons is equal to number of holes. That's intrinsic. N-type is when number of electrons is larger than number of holes. And P-type is when number of holes is larger than number of electrons. Okay, so this layer is P-type, number of holes is larger than number of electrons. And here, there's a region where we cause number of electrons to be larger than number of holes. And that's why we call it an inversion layer. Because originally, the layer was P-type, and this whole thing was P-type, and we have made the surface N-type. We made the surface rich in electrons, number of electrons is much larger than number of holes, and it becomes an N-type kind of a surface here. And therefore, we say that it's an inversion layer here. We form an inversion layer, and also this is a channel now. So it's a channel of thin layer of electrons. It's a channel, so my source and drain get connected through the channel, and current starts to flow. Okay. The basic principle behind this is this one here. Number of electrons into number of holes is equal to Ni squared. So what is really happening is, let me go and look at it in a little bit more detail here. So the heart of this MOSFET that you see here, this is for basically for a source, as a source of carriers, and this is for collecting, for making a transistor. The heart of the MOSFET is this metal, oxide, and semiconductor, which is a capacitor here. So metal, oxide here is a capacitor here. So if you want to understand, if you go and read books on MOSFET, the first thing that the books will do is talk about how this system works, how a MOS capacitor works, because that's where, all the interesting things are happening in terms of creation of a channel here. So what we are seeing here is that obviously we are able to modulate the conductivity. We saw that if you apply initially positive voltage, what happens is all the holes go gradually. You create more and more depletion here. Eventually, you create a inversion layer at the surface here. For the sake of discussion, let's consider the following. Suppose I have my P-type semiconductor, which is doped 10 to the power 16. Okay, 10 to the power 16. So approximately the number of holes is close to 10 to the power 16. The number of electrons in my system is Ni square by Na. Ni square typical value is 10 to the power 20, and divided by 10 to the power 16, so it's going to give me 10 to the power 4. So starting P-type semiconductor is what? 10 to the power 16 holes and 10 to the power 10 to the power 4 holes, electrons here. So that's the starting picture. Now, as you apply larger and larger gate voltage, what do you do at the surface? You push the holes away. Right? We saw you push the holes away. So what will happen? From an initial value of 10 to the power 16, the number of holes at the surface will become 10 to the power 15, 10 to the power 14, 10 to the power 13, 10 to the power 12, gradually they will start decreasing, right? As they start decreasing, okay, so let's see whether this picture makes sense here. So keep this in mind. I'm talking right now about the surface only, okay? So at the surface, everywhere in my system, Ns, number of electrons into number of holes, has to be equal to Ni square, 10 to the power 20, okay? So, and this is, I'm saying I'm increasing the gate voltage steadily. And this is what is happening in my system. When my gate voltage is 0, number of holes in my system is 10 to the power 16. Number of electrons is 10 to the power 4. That's my normal p-type semiconductor. As you go along this axis here, as you increase the gate voltage, what do? You push holes away from the surface. So holes become 10 to the power 15. When holes become 10 to the power 15, the number of electrons become 10 to the power 5. Because the product has to be equal to 10 to the power 20. Okay, so they become 10 to the power 5. You keep on applying higher and higher gate voltage. What is happening? The surface is getting more and more depleted of holes. Eventually, you come to a stage where number of holes at the surface is 10 to the power 10. And number of electrons is also 10 to the power 10. What has the surface become? Intrinsic. Number of electrons is equal to number of holes. So note, here the surface was p-type. And here the surface has become intrinsic. Now, you keep on increasing the voltage. So number of holes will become 10 to the power 8. Number of electrons 10 to the power 12. And as you keep on going, eventually you come to a stage which we call as the threshold voltage, where you have made number of holes 10 to the power 4 and number of electrons 10 to the power 16. This condition where you see that it's a total inversion that you have caused. The starting material was p-type, number of holes was 10 to the power 16, number of electrons is 10 to the power 4, and now you have done exactly opposite. You have made number of holes 10 to the power 4, number of electrons 10 to the power 16. And this is the place where we say threshold is called threshold voltage, where my surface is now become inverted. Actually, inversion occurs here, right here. You can see it's already become n-type. But here it has become totally opposite of what was there in the bulk. Okay? And if you apply even larger voltage, what happens is you start putting more and more electrons at the surface. So you can make number of electrons at the surface 10 to the power 17, 18, 19. It keeps on increasing. Okay? So this is the basic phenomena that is occurring in your metal oxide system. By applying a gate voltage, you can make the surface. Note that if I had gone negative, gate voltage negative, what would I have done? I would have made the surface even more number of holes at the surface. So I can actually increase the number of holes also. If I go negative, I can make 10 to the power 17, 10 to the power 18, 10 to the power 19. So note with the gate voltage how I can alter the number of holes or electrons at the surface. We can go from a surface which is p-type to a surface which is intrinsic to a surface which is n-type, and surface n-type here, surface which is strongly n-type. Large number of electrons at the surface here. Okay? And therefore the transistor that we are talking about is a transistor which is operating in this region here. Because my source and drain are n plus, and therefore when I go into this particular region, my surface has become n-type, and I have a channel which connects my source and drain here. So this is a schematic illustration in a graphical form what is happening here. As you increase the gate voltage here, hole density is steadily decreasing, electron density is steadily increasing here, and threshold voltage is the point where my electron density at the surface has the same value as hole density in the bulk. Okay, so that is what we call as the threshold voltage. All right. Now, so that's the basic operation. Now, what happens is I've been telling you that when you apply 0 volt here, when you apply 0 volt here and you apply 0 volt here, what you get is, the surface is p-type. The surface is p-type, but actually what happens is, if surface is just like the bulk, right? But actually what happens is, when even if I put 0 here and I put 0 here, there is an internal field in my system, internal voltage and field in my system. Okay, I'll not go into the details, but you can imagine that when I took a p-type and an n-type semiconductor and made a p-n junction, We didn't apply any voltage, right? And what was there inside? There was a voltage, which we call as built-in voltage, and there was a field. So similarly, the basic idea there is whenever you take two different materials and you put them into contact, you end up getting a what we call as contact potential. Okay. So even though I put it to ground and I put it to ground, what happens is typically that there would be some kind of a field already there in my system. And that field is called built-in field, and the voltage is built-in voltage. Now, if there is a field in my system, you can imagine the surface will not be like the bulb. The surface can become more p-type, or the surface can become depleted of carriers. Anything can happen depending on the nature of the field that is there inside. So we say that we have a voltage called flat band voltage. Flat band voltage means, note that we are saying all the conduction band and the valence bands are all flat. Flat means no field, zero field. Okay. So what we are saying is that you need to apply a voltage called flat band voltage to cancel the internal field. Okay. So you have to apply a voltage called flat band voltage to cancel the internal field and make the net field inside my system zero. And when net field inside my system is zero, my surface here is just like the bulb. The whole thing is a p-type semiconductor. So you need a voltage here. In general, you need a voltage here, which we call as flat band voltage. So our reference point is what? Flat band voltage. Now, if I make my gate voltage positive with respect to flat band voltage, what will happen is I'm applying a more positive voltage. So what am I doing? I'm applying a positive voltage. I'm applying a field in which direction? From here to the ground. Net field. If I make VG larger than flat band voltage. Okay. So I'll have a net field which is going from this terminal to the ground here. If I apply a voltage less than the flat band voltage, I'll have a field which is going up here. Because at this gate voltage, the net field is zero. Okay. So this is the situation then. For voltage larger than the flat band voltage and voltage less than the threshold voltage, I have what we call as depletion. Anything larger than the flat band voltage, the field is pointing down and is pushing the holes away. And is pushing the holes away, so all this region is depleted of holes. But my voltage is less than threshold voltage. What was the meaning of threshold voltage? It's the point where I have sufficient number of electrons at the surface. Okay. Now, if it is less than threshold voltage, which means I don't have enough electrons. I have electrons, but not enough. And therefore, neither do I have holes here, large number of holes, or neither do I have large number of electrons. And therefore, we call this region as a depletion region. Number of electrons here and number of holes also, both are less than the number of acceptor atoms that you see. So the whole region is depleted of carriers. Electrons are also not there and holes are also not there. Okay. So we call this depletion region. Between these two limits here. Voltage has to be larger than flat band and voltage has to be less than threshold. Okay. Holes are depleted from the surface here and number of electrons may be larger, but electron density is also small. Voltage greater than threshold voltage. If you apply VG larger than threshold voltage, then of course you have large number of electrons at the surface. There is a depletion region here, but there are large number of electrons at the surface. Okay. And so this is what we call as strong inversion. It's heavily inverted. Number of electrons here may be 10 to the power 18, 10 to the power 19, as large as that. So that's another condition here. Number of electrons is much, much larger than whatever is the background doping here. And then we have a region called VG less than flat band. Now the fields are pointing up. The fields are pointing up. So what you do is you have more holes at the surface here. We call this region as accumulation. Because already the surface was p-type. Now it's even more p-type. You have more holes at the surface because the voltage, the field is pointing up. So it attracts more holes to the surface here. Okay. So we call this region as accumulation. So you can see three distinct regions here. Depletion, where I have hardly any carriers at the surface here. Neither a lot of electrons nor a lot of holes. Strong inversion, lot of electrons at the surface. And accumulation, lot of holes at the surface. Okay. So that's the background that we need. So now what we have is MOSFETs can be classified into two categories, depletion mode and enhancement mode. We just saw that you need to apply a voltage to create a channel, and that's why we call it an enhancement mode transistor. And each one of them can be N channel or P channel here. And these are the symbols here. So we'll primarily be concerned with N channel, with enhancement mode transistors here. And you can see the symbol. For an N channel, you have drain, source, body, gate here. The arrow is pointing in and the arrow is pointing out here, which you'll see from the next diagram here. Okay. All right. So basically the body is P-type and the source is N-type here, or the channel is N-type here. So if you look at a PN junction, is pointing, is pointing into this particular layer here. Okay. So the arrow points in this direction. The dotted line indicates that it's an enhancement mode transistor, that when you don't apply any gate voltage, you don't really have a channel. You have to apply a voltage larger than threshold voltage to create a channel here. That's why the dotted line here, and the arrow, of course, denotes this, and you have drain, source, and body here. Many times what we do is we use a simplified symbol here, where drain, gate, and source, unless it is explicitly stated, we'll assume many times that body is connected to the source. Body is shorted to the source here, and this is a simplified symbol, 3-terminal symbol here of a N-channel MOSFET here. So that's your N-channel MOSFET. Now, if you see the N-channel MOSFET, you are seeing that the source is here, drain is here, gate is here, and the body is here. Quite often, you don't, it's inconvenient to take a body from the opposite side, so you can make take a contact of the body right at the top. So you create a layer of P plus, all this body is P-type, and when you create a layer of P plus, it makes a good contact to the P-type here, and so you have a body contact right at the top. So you have source, you have drain, and you have a body right at the top here. P-type is over here, is just the complementary part of N-type here. So it's N-type body here, and P plus source and drain. Gate is here, oxide is here, and body is here. Okay, and the symbols are just complementary here. Okay, now typically what you have to do is you have to make N-type and P-type both on the same silicon. So many times what happens is the silicon itself is P-type, starting silicon, and if you want to make a N-type transistor, a P-type transistor, so what you do is, this is your main silicon, that yellow region that you see here. In this region, what you do is, you create what we call as a N-well, a well of electrons here. And we call this N-well, and within this well, you make now P plus here, and this is a P-channel MOSFET, and this is the body contact. Okay, so now the next one will show you both an N-type and a P-type transistor, made on the same silicon substrate here. This is a P-type substrate. This is your N-channel transistor, source, drain, body, and this is a P-channel transistor here. P-channel is made in a N-well here. So you create first an N-type layer, and within that N-type layer, you do P plus and N plus and all that, and you make your source, drain, and body. Okay, so that's an N-type and that's a P-type. Now suppose I make two N-type and two P-types. Okay, two N-types and two P-types. What differences do you note here? Suppose I were to make another N-type MOSFET. If I were to make another N-type MOSFET, do you see that both N-type MOSFETs will have the same body potential? Both N-type MOSFETs will have the same body potential, because the body that you see here is common to any number of N-type transistors that I make. Because when I make another one, instead of this one, I'll make another one here, and the body is the same for all N-type. While the body can be different for different P-type. I can make a P-type transistor inside an N-well, and I can create another N-well here and make a separate P-type transistor. And then the body is separate for the P-type transistors. That is very important. We'll see later on the consequence of that. Okay. Oh, I have the figure here, so you can see. Two NMOSs side by side. Two NMOSs side by side. Two PMOSes side by side. Won't the two, will the two NMOSes interfere with each other? Will they interfere with each other, or are they isolated? How will they interfere? Body is same, fine. That we have seen. Aside from that, will current flowing between source and drain here, or the voltage applied here, have an impact on this side? Normally, when you make two transistors, you want them to be isolated, right? The characteristics of one transistor, whatever voltage you apply, should not affect the current flowing here. Are the two isolated? Are the two transistors isolated? Or are they connected? Okay, think about it. Let's stop here.